chip-scale molecular clock, which we believe to be a very promising solution for miniature timekeeping devices with extremely low cost. Here I'm representing my clock team at MIT. My students Cheng, Wang, Mina, Xiang, Zhihu, and also Jimmy Mawdsley. So they are the people who make this work possible. So this is the outline of the talk. So first of all, I will talk about the background of this research, and then we will focus on the basic principles of the chip-scale molecular clock, which is basically based on terahertz rotational spectroscopy, as well as the other enabling technologies, which is basically the results of Moore's law that has lasted for multiple decades. And then we will present two clock prototypes. One is based on lab-scale instruments, and then the other one is based on a fully integrated CMOS chip. I will show some experimental results, and finally I will conclude the talk with some ideas about the future directions. So to begin with, here I show you the comparison of various clocks. This graph is adapted from the figure by Dr. Cheng and also Dr. Dongli in NIST. So as we can see from here, the crystal oscillators, they basically generate ppm level stability. They burn very little power, and they are very cheap. So that's why they enable mainstream electronic devices like cell phones and computers. However, because of the fact that the output frequency is not locked to any invariant physical constant, the stability is not good enough for some high-end applications such as large-scale networking and also inertial navigations. And then, of course, we can use atomic clocks to enable those applications, but then the consequence is the power is very large, multiple watts, and also the cost is very high, $1,000 or even, for example, for the Maser, it could be $1 million, and they're also very big. At the same time, one important trend that we see from the great advances of sensing and communication technologies is there's a very strong demand for miniature timekeeping devices with very low cost. For example, here I show you the evolution of cellular networking. As you probably know, for the 3G networking, there's only a requirement for the synchronization of frequency. And then for 4G networking, there's a timing synchronization with a tolerable error of roughly a few microseconds. And now for 5G, which is a very hot topic right now, due to the requirement of the carrier aggregations and also the accurate localizations, multiple base stations have to work together, and the timing requirement is within 100 nanoseconds. So that's actually very hard because, of course, we can use GPS to synchronize multiple base stations together, but to really make the network reliable, we need to have internal clock, which behaves as the holdover for the timing. So for a 1 hour holdover with a timing error smaller than 100 nanoseconds, the stability needs to be smaller than 10 to the minus 11. So the difficulty in here is that for 5G networking, we need to have a very big density and a large number of base stations, and that means these infrastructures become very sensitive to the cost of these clocks. One very well-known and successful example for miniature stability timekeeping device is, of course, the chip-scale atomic clocks, or CSAC. So here I show you the one from NIST and also the one from Microsemi. So using a very low power consumption and also small size, the CSAC delivers stability at the order of 10 to the minus 11 at 1,000 seconds. But the problem is, due to the complicated construction, which is the hybrid construction of electro and photonic structures, the price is very high. It's over $1,500. So because of this complication of construction and also high price, the application range for CSAC is limited. And here I show you some more details about why the CSAC is complicated. For example, we need to encapsulate cesium gas inside a cell with buffer gas to immobilize the atoms. And then we need to have a very precise VCSEL to probe the transition. And then photodiode. And because of the fact that the VCSEL is sensitive to the temperature change, we need to have a good heater and also a temperature stabilization control loop. And eventually, the transition of these atoms by itself is very sensitive to the magnetic field, so we also have to get a very good magnetic shielding. In comparison, what we're proposing here, which is the chip-scale molecular clock, has a much simpler construction. In here, we encapsulate some carbonyl sulfide molecules inside a single-mode terahertz waveguide. And then we use a very small and low-cost CMOS chip to generate a sub-terahertz wave, and that wave is phase-locked to a crystal oscillator. And we use this wave to probe the rotation frequency of the molecule and then build this frequency control loop. This way, another clock is built, and what we can see in here is that because of the fact that the chip is very, very low cost, so this solution essentially can be very affordable. And of course, we are not the inventors of a molecular clock. I'm pretty sure you know that the very first atomic clock is actually a molecular clock. So back in 1940s, people used the inversion spectrum of ammonia to build the clock. Basically, this transition frequency happens at about 24 gigahertz, which is based on the tunneling of the nitrogen atom through the hydrogen atoms, hydrogen planes. So there are, again, similar advantages. For example, it's all electronics, meaning that the construction could be pretty simple. But of course, due to the fact that the absorption intensity of inversion spectrum of ammonia is very weak, they basically need to have a very long gas cell. So as you can see from the top right side of this figure. And also because the frequency is not high enough, the diameter of the waveguide will be very big. So due to these two factors, the gas cell is actually very bulky. And of course, back in 1940s, it is really hard to generate frequency at this 24 gigahertz. So that's another layer of difficulty. And that is why this very first atomic clock doesn't deliver very good stability. And based on our literature survey, it seems that the related research eventually dies out in around 1970s. Okay, so let me show you how we can revitalize the molecular clock using the terahertz rotational spectroscopies and also the state-of-the-art terahertz electronics on CMOS chips. So first of all, I show you some basic principles of rotational spectroscopy. Essentially, this only happens for the polar molecules where you have a dielectric dipole. And then when we shine an electromagnetic wave onto the molecule, the wave will drive the molecule and make it rotate. And then when the frequency of the EM wave matches the transition frequency between two energy levels of the rotation energy, then resonance happens. So inside a transmission mode spectrometer, we can observe an absorption line. And of course, the energy of the rotation is quantized. In specific, for linear molecules, we see that the energy is distributed in a quadratic way. And then if you calculate the transition frequencies in the nearby two levels, we can see that frequency-wise, they are equally spaced so that you have multiple choices for the probing. And it turns out that the spacing is determined by the mass and also the bond structure of the molecule. For the molecule that we use in here, which is a carbonyl sulfide, the frequency spacing is about 12 gigahertz. For other molecules, for example, hydrogen cyanide, which is lighter, the frequency spacing can be pretty large. For example, that is 80 gigahertz. So that's why you have the spectrum shown on the right. Here, when the frequency is low, as the frequency goes higher and higher, since we have more sub-levels associated with different magnetic quantum numbers that could contribute to the overall absorption, we see that the intensity increases with the J number, or the angular momentum quantum number. And then the absorption plateaus at about 500 gigahertz, and then going forward, because of the Boltzmann's distribution, the absorption goes down. So this graph shows you that in order to probe the rotational spectroscopy, the best frequency to work with is about a few hundred gigahertz. And due to this nice feature, previously people used terahertz spectrometers to detect the gas. And the most well-known application is astronomy. Basically, places like JPL, NASA, they use terahertz spectrometers to analyze the interstellar dust composition. Of course, nowadays, people are also very interested in using terahertz spectrometers to detect the hazardous and also analyze the breath of human beings. Shown on the right is one example. People found that there's a very strong correlation between the concentration of acetone inside our breath and also the blood glucose level. So if we have a terahertz sensor that can detect the concentration of acetone, then there's a non-invasive way that could tell us the blood glucose level. So in my group, we investigate the terahertz spectroscopy extensively. And what we found is, in addition to the gas sensing, some of the molecular transitions could be very good candidates for timekeeping. For example, here I show you the measured transition line of carbonyl sulfide at 267 gigahertz. So what you can see is that if I have a low pressure, then the transition line is Doppler limited. So the quality factor could be as high as 5 times 10 to the 5th. So here there's no buffer gas. And of course, once we start to increase the pressure, the absorption starts to decrease, continue increases, but then plateaus. But due to the broadening of the pressure, the line width starts to also grow. So the best pressure to work with for the clock is basically at the boundary between the Doppler limited region and also the pressure broadening limited region. And the second factor for this clock is that we really want to encapsulate these gas inside as small as possible gas cell. And the smallest possible implementation of the gas cell is the single mode waveguide. So on the left, I show you the gas cell with a cutoff frequency of 200 gigahertz. So what you can see is that the cross-section of the gas cell is only 1 millimeter by half millimeter. And fortunately, even with this very small size, the wall collision broadening is not very significant. So it's roughly 7%. And of course, there are other reasons that we choose OCS due to its better stability against environmental changes. So later on, I will introduce more about this. And we also see that OCS has a very good property that is in favor of miniaturization. And there are multiple reasons. For example, the dipole moment of OCS is very large. That means the absorption could be very strong. And also, as we go to sub-terahertz range, there are over 100 sublevels that contribute to the absorption. And because of that, now if you do the comparison between OCS absorption as well as the ammonia absorption, what we can see is that now we have over 100x higher absorption. So that potentially enables a much smaller gas cell. So we did some more calculations regarding the OCS gas volume that is needed to achieve certain absorption contrast. Here the standard is 30% absorption contrast. So what you can see is that due to the fact that the waveguide cross-section area is inversely proportional to the frequency square, and also if you increase the frequency, the absorption intensity increases rapidly. Then going to, for example, 230 gigahertz, we see that the total volume needed, and that is the ultimate limitation for the gas cell, is smaller than 100 millicube. And then if we can further increase the frequency to 550 gigahertz, then the total volume needed is even smaller than 10 millimeter cube. So that promises a very good future for the miniaturization of the molecular clock. So now we have the reference gas. We have small gas cell. One big missing puzzle is the terahertz electronics. As you probably know, there's this very well-known terahertz gap, which tells people that it's going to be very hard to generate terahertz power and also detect the terahertz signals using mainstream electronics. And that is potentially why most of the terahertz instruments nowadays are still very big and also very costly, as I can show you in here. But in order to enable this chip-scale molecular clock, we really need some terahertz component that is extremely small and extremely low cost. And the most ideal case is a CMOS chip, which is used for implementations of computer and also cell phone electronics. But the question is whether CMOS chip is able to do this work. And fortunately, over the past few decades, the performance of these silicon devices improved dramatically. Here I show you the cutoff frequency of these CMOS devices, as well as the cutoff frequencies of BiCMOS silicon germanium transistors. So what you can see is nowadays, the cutoff frequency is mostly above 200 gigahertz. So that enables us to reach the low terahertz range using harmonic generations. And as a matter of fact, some recent advances in the device, for example, this Intel 22 nanometer FinFET and also IHP 130 nanometer HBD process have a cutoff frequency that is even above 500 gigahertz. So that will enable very efficient power generation and detection in the low terahertz range. And because of these devices, nowadays we can comfortably generate very good terahertz signal. So here I show you some of the recent CMOS and BiCMOS work in this field. So, and some of those are demonstrated by my team at MIT. So what you can see is that in the low terahertz range at about 0.3 terahertz, we are able to generate a few milliwatt already. That's radiated power. And even at 1 terahertz, now we are able to generate almost 100 microwatt of radiated power. So that's one good news. And then the other news is that we can also perform very high precision frequency and phase control at this frequency. For example, we have demonstrated the very first terahertz radiator array with integrated PLL, phase lock loop. So there's, in general, a trend of probing these reference gas at higher and higher frequency, and we have seen so many optical comb there. Here, this is one way of phase lock the terahertz signal with the crystal oscillator. So that's another enabling technology. And finally, the signal detection. In the past, in this field, the detection is driven by the imaging applications. So now the whole field have demonstrated both the square law detectors as well as the heterodyne detectors. So the square law detectors nowadays have noise equivalent power at about 10 picowatt per root hertz. And the heterodyne detector is much more sensitive. For example, in this case, which integrates 32 heterodyne receivers with the built-in LO component, the detection sensitivity is almost 10,000 times better than the square law detectors. So now we have all the components that we need. And eventually we can bring all these components together and construct a terahertz spectrometer. So this is just one example from my group. So in here, because here the spectrometer is targeted at gas sensing, so we want to cover a very wide frequency range. So in this particular work, which is based on what we call bilateral dual frequency comb spectrometer, inside each chip, we generate 10 equally spaced frequency lines, and also the chip simultaneously detect another 10 frequency lines from another side of the spectrometer, and that is generated by another CMOS chip. And that way we have 20 frequency lines that can detect this 100 gigahertz bandwidth. So here, the coverage is it ranges from 220 gigahertz to 320 gigahertz. So this chip is implemented inside a 65 nanometer CMOS process. As you know, nowadays the most advanced CMOS technology node is 7 nanometer and even 5 nanometer. So this is a very old process, but can still do the work. The total radiated power is over 5 milliwatt. The sensitivity is smaller than 1 attowatt per hertz. And here's one demonstration of the terahertz spectrometer using these CMOS chips. So here we inject OCS and also acetonitrile gas inside a gas cell. And what we can see in here is that this dual frequency comb CMOS spectrometer are able to detect all the fingerprints of this gas mixture. Because of this very wide frequency range, this spectrometer can detect almost any polar molecule, which is heavier than hydrogen cyanide, and also the sensitivity is better than ppm level without any pre-concentration. So that's very encouraging. So now we have the reference gas, we have a very small gas cell, and also we have this CMOS platform which can detect all of these transitions. So now it is time for us to build the clock. So let me show you how. So before doing that, we use the small gas cell and couple that with some commercial terahertz instruments just to demonstrate the idea. So here, the gas cell, again, it has a cutoff frequency of 200 gigahertz, and the total length of the gas cell is 14 centimeter, but since the waveguide is folded, so the actual volume is very small. We use a VDI network analyzer frequency extender to generate signal at 267 gigahertz to probe the OCS transition at that frequency, and then use another VDI frequency extender as the receiver to detect the absorption, and then we close the loop. So here what I want to mention is that the output frequency of the terahertz transmitter is wavelength modulated, meaning that when the center frequency is close to the transition frequency, due to this wavelength modulation, we generate a baseband signal that has the fluctuation at the same modulation frequency. In here, it is 100 kilohertz. But due to the shape of this transition line, the output baseband signal from the receiver also carries the distortion, which is the harmonic components. And then using a locking amplifier, we can detect different harmonic components. So here, because we want to utilize the zero crossing point of the spectral line, we use the odd order harmonics. Shown on the right is one example, which is the detection at fifth order harmonics. In this setup, the total measured signal-to-noise ratio of the spectral line with 1 second integration time is 87 dB. Using the fifth order harmonic detection, the SNR drops to 71 dB. And there's a very big reason that we want to use the high order odd order harmonics. And that is because inside this entire setup, we have a weak internal reflection of terahertz wave inside the single mode waveguide. And because of that weak reflection, we form a standing wave inside of the gas cell, which means that now the transmission has a weak dependency of the transmission frequency. So now, if I use wavelength modulation, which is essentially detecting the various order of derivatives of the spectral line, what you can see is on the top, once I have this baseline tilting, then the generated first order spectral line carries offset. So that's bad because ideally, even if I change the pressure and also the temperature of the OCS, the center frequency of the transition line shouldn't change. But now, because the total spectral line measured is the superposition of the baseline tilting and then this ideal OCS transition, what we can see from the figure on the bottom is that now the center frequency drifts once you change the pressure and also the temperature. Fortunately, by using high-order, odd-order harmonic spectral detection, this effect is greatly reduced because the change of the baseline is very gradual. So once we use high-order detection, which is equivalent to taking the high-order derivative of the curve, then this gradual change of the baseline is greatly reduced. Okay, so eventually I show you the measured Allen deviation of this instrument-based prototype. So if we use fundamental mode detection, then we see that it generates a very good short-term Allen deviation. At 1 second, it is below 10 to the minus 10. However, since here this homemade gas cell has a pretty large leakage, as the time goes by, the pressure changes, and then due to the baseline tilting, the Allen deviation becomes worse. Fortunately, if we use the fifth-order harmonic, we see that there's a trade-off in the short-term Allen deviation, but the curve can continue integrating all the way to 1,000 seconds, and that generates Allen deviation, which is around 2 times 10 to the minus 11. And the time domain measured output shown on the bottom is a much more straightforward way to show that this molecular clock regulation loop basically corrects the drift of the crystal oscillator. We also characterize the stability of the OCS transitions with the presence of temperature change as well as the magnetic field that is applied externally. So here's the setup. We use a temperature-controlled gas cell, and then outside of this gas cell, we use a Helmholtz coil, which can apply 75 Gauss of magnetic field, which is really strong. And here are some preliminary results. Due to the outgassing and also the leakage of the gas cell, right now we are not able to increase the temperature by too much, but at least between 45 to 55 Celsius, what you can see is that the deviation of the output frequency is pretty small. So right now, the temperature coefficient is about 2 times 10 to the minus 10 per Kelvin. Again, here there's no oven, there's no temperature compensation. It's just the clock by itself. So even with this preliminary result, it seems that this molecular clock is able to deliver 1 ppb stability over 100 Kelvin range when back-end temperature compensation is applied. Of course, more measurement should be done. And here is some measured drift with the presence of this very strong magnetic field. So what we can see is that the overall drift is smaller than 5 times 10 to the minus 10. Here, there's no magnetic shield, and the reason why we have this very big, robust against the magnetic field is because OCS has very small magnetic dipole. If you think about it, the rotation of this dipole, electrical dipole, carries a very small magnetic dipole. So actually, the gyro factor is about 0.03. And that couples with the center frequency of 260 gigahertz generates a very small first-order Zeeman shift. And the other reason for this robustness is because here we use all the sublevels for the absorption. And the interesting part is for those sublevels which have a first-order Zeeman shift, they basically shift towards 2 opposite directions, and then they cancel each other. So only the second-order shift matters in here. And we actually did simulations based on the theoretical drift for each sublevels and also their intensity respectively. And what we can see from the right is that the intrinsic relative shift of the OCS center line with the presence of a 75 Gauss magnetic field is about 10 to the minus 13. So it's very robust against the magnetic field. So now I show you some results based on the instruments, but that's still very far away from our promise, which is the chip scale molecular clock. So the question is whether we are thinking about is fact or scientific fiction. And the best way to verify that is to actually build the clock. So my student goes ahead and built this CMOS-based chip-scale molecular clock. So here, this chip set includes the transmitter and also the receiver. Inside the transmitter, there's an integrated sub-terahertz phase lock loop with 10 to the minus 12 frequency tuning resolution. And here we don't use the wavelength modulation. Instead, we use the frequency shift keying modulation, meaning that the output frequency is hopping between two frequency points, and then we dynamically detect the edge of the same spectral line, and then generate the error signal. Inside the receiver side, there's fully integrated locking amplifiers and all the other control circuits. So here's the package. The chip is wire bonded to a quartz probe so that the wave can be coupled into the waveguide gas cell. In the simulation, the coupling loss is about 1 dB. The overall package is about a bottle cap size. Right now, the size is limited by the size of the PC board, as well as the need for connecting to the vacuum pumping system. But again, let me remind you that in the end of the day, the final limitation for the size of the gas cell is how much OCS you need to encapsulate inside the gas, the waveguide, and that is smaller than 100 millimeter cube at this frequency. And here are some electrical measurement results. The total DC power of the chip is only 66 milliwatt. The reason why it's not as high as many people expected for terahertz system is because here we don't need to generate very high terahertz power. In our study, we show that once the probing power is over 0.1 milliwatt, then we start to have the power broadening. So that in turn allows us to burn less power so that we don't saturate the gas. Because of this wire bonding-based coupling, we actually experience pretty big coupling loss in the actual experiment, and that is unexpected. In the measurement, the output power is 10 dB lower than simulated. The noise sensitivity, the detection sensitivity is also 10 times worse. So now we have identified the problems for this bond wire coupling, and some new designs are on the way based on the on-chip antennas, which can directly couple the wave into waveguides. But even with this 20 dB degradation from the previous prototype, we can still use the chip to measure dispersion curve with a signal-to-noise ratio of 53 dB. So that's still a very clean wave, a very clean curve. And then the measured Allen deviation is roughly 4 times 10 to the minus 10 at 1,000 seconds. So with improved chip-to-waveguide coupler, the Allen deviation can further be decreased by roughly 10 times. And of course, future design will also incorporate wavelength modulation instead of FSK modulation, just to correct the temperature and pressure-induced drift. Another part of the plan is to use the state-of-the-art CMOS technology so that we can further reduce the DC power from 66 milliwatt to below 30 milliwatt. Okay, so finally the conclusion. So here we demonstrate that terahertz rotational spectroscopy is a good alternative approach to provide invariant physical constant for timekeeping. We show that miniaturization is possible. The transition line has pretty good stability, and most importantly, the whole implementation can be based on very low-cost CMOS chips. And our first generation of the prototypes shows that the Allen deviation could be on the order of 10 to the minus 11 at 1,000 seconds. And finally, just one vision that I would like to share. We believe now a monolithic CMOS molecular clock becomes possible because now these waveguide can be integrated inside the same chip through the MEMS technology. Actually, people have already demonstrated micro-machined silicon terahertz waveguide So by encapsulating OCS gas inside this integrated waveguide, now we have a true on-chip molecular clock. With that, I would like to conclude my talk. I would like to thank these team members, collaborators, and the sponsors. Thank you very much.
So thank you very much for this very interesting talk, and we can take the time to have a few questions. Yes, back there, please.
If your clock is based on a single rotational translation, what are the rotational clock numbers for your rotational translation of the clock translation? Or what vibrational band your clock translation is?
Are you asking the optimal quantum number for this?
Rotational quantum number of the clock.
So for the, I actually have the data in the previous slide. So for the lab scale clock, we use the transition from 21 to 22. And for the chip scale clock, because we want to achieve better energy efficiency, we lower the frequency to 230 gigahertz, and that is related to the transition from 18 to 19. No, this is a pure rotational bands.
Yes, what's the vibrational quantum level?
What vibrational level is the rotation spectrum?
I think it's still the ground level. Yeah.
That's the ground vibration.
Yeah.
We had another question here.
It looked like the line width of that rotational transition was about a full width of maybe 2 megahertz.
It's about 1 megahertz. Okay. The smallest is 500 kilohertz.
Do you know what the 3 dB point width is of your phase-locked VCO?
3 dB point of my phase-locked VCO. You mean the line width?
Huh?
You mean the line width of the output of the VCO?
Phase-lock it, yeah.
That's very narrow. It's Hertz level.
Hertz level.
Yeah. So it's way smaller than this.
Okay, we have one more question by John.
That's a good question. So at this moment, we are not 100% sure because, terahertz rotational spectroscopy has been well studied, but based on our literature survey, no one has ever looked at the resolution down to this level. So it's at this moment it's a still open question. Yeah.
One more question.
Related to this question, which physical phenomena you expect to limit your stability between 100 to 1,000, 10,000 seconds? What are the main sources of frequency?
So if you are asking about, because right now it's based on, it's simply due to the non-ideal gas cell, the leakage, the baseline tilting. We actually did the calculation based on the pressure-induced drift, from a theoretical level. That is about, so eventually, because it's encapsulated, so the pressure change is due to the temperature change. So if you translate everything to the temperature coefficient, it's about 10 to the minus 12 per Kelvin.
And that's the only physical phenomenon that you expect to
That's so far the at least it's going to be the dominant factor that will limit the stability.
We can take one more question, please there.
What dominates your 66 milliwatts of power?
Yes, the output is 10 megahertz. Actually 60 megahertz. Our crystal is at 60 megahertz. So the power is dominated by the multiplier chain to generate the terahertz signal, as well as the other phase lock loop components. And that is why we have the confidence that, by using more advanced CMOS technology nodes, especially those with cutoff frequency that is way higher than, this one, the cutoff frequency is 200 gigahertz. So if we use, for example, cutoff frequency of 500 gigahertz, then we believe this power can be dramatically reduced, because then you can use fundamental mode. You don't have to turn to the harmonic generation. Yeah, 65. Yeah.
Okay. Any more questions? If this is not the case, let's thank the speaker again for this nice talk.